So now group two, are
Hi, how
you
you doing?
ready?
As ready as I'm going to be. Tough acts to follow. Give me a moment there.
Yeah, sure.
Right, so girl, I will put the timer this time, okay?
Yep.
Okay, you can see my screen there without issue, yeah?
Yes,
Yes.
we do.
Excellent, right. Good evening, everyone. Welcome to the FCP presentation for Group 2. Today we're going to talk through automated cost efficiency reporting and bill of quantity / value engineering development for infrastructural utilities design in an existing urban context using mobile mapping data semantic segmentation. So just because of the time limitations today, we're not going to go through all of this. So very quickly, I'm going to go through the introduction, the problem statement of the existing workflows. We're going to hypothesize what the idealized workflow should be. We're going to go through the results of a case study that we actually undertook with real-world example to compare against. And then we're going to go through very high-level to completed data set and process maps and onto the synopsis and findings, and then all the workflow questions we can maybe deal with in the Q&A afterwards. So going to the introduction very quickly, this deals with the AI applied to cost estimation and project planning specifically as per the ziggurat requirements. And this process here, as a series of images just to describe high level what we're trying to achieve, is to take panoramic mobile mapping data images, segment the material classifications within those, then publish those as vector-based shapefile graphics onto a GIS 2D map overlay, which can then be automatically brought into a vector-based design environment where design options can be iterated for various service runs crossing the different material properties, and then all of that design data collated, exported automatically into a CSV file into a vertically trained large language model that'll auto-produce the cost-benefit analysis for the design, which will produce a bill of quantities on request, and also give you iterative value engineering insights as you need them. So the problem statement with the existing workflows, looking at the right-hand side there, you can see an example of a high-level design for a fiber optic route nominated in Germany at the moment. And the existing workflows for the generation of this design do not utilize mobile mapping dataset to any great degree, and as a result, they lose capacity for geospatial insights that are valuable. The predefined design parameters oversimplify urban complexities, particularly in the European context, because cities tend to be so old. And the traditional cost estimation relies on manual surveys and subjective assessments. As a result, the cost estimations lack granularity and accuracy, and this has a knock-on to a potentially 50% cost increase on average as we go from the high-level design through to construction. So what the anticipated cost is tends to climb by up to 50% by the time the construction is realized. So looking at a very quick sample of the case study, on the left-hand side, we can see a city block in Hamburg that was nominated, which we already have existing time horizons for the development of services through this area. And on the right-hand side, you can see a manually segmented image with manual layer mapping information aside to it, which is a very slow process. So looking at the historic workflow, basically it's broken down into 4 distinct stages. There's a data capture, data processing preparation, design development, and costing, value engineering, and bill of quantities delivery. So on the data capture, this is manually derived under topographical surveys and manual GIS overlays, and the mobile mapping data is generally not touched. Data processing and preparation involves taking that manually derived topographical information and then preparing those surveys to bring into the vector-based design environments. And there's often friction with that, including information gaps, RFIs, requests for additional information, and so forth. Then this information is passed through to the design development environment where the engineering team will develop their design options. Again, there's further clarifications needed and frictions through RFI processes. And then there's a manual identification of the core data required for the costing exercise that has to be identified, measured, and extracted. Then from there, going into the costing exercise, you basically have a manual review of the data extraction, further RFIs, manually measuring all of the utility runs and their various surfaces that they cross, and then assumptions and contingencies to fill in the knowledge gap so the costs are actually there for procurement. So looking at the actual example use case for Hamburg, that one city block there took 3 months to realize all 4 of these stages in the existing workflows. So how do we resolve this? What is the idealized workflow for this? What do we hypothesize? So in typical engineering fashion, we took all the things that we thought were high friction and got rid of them. We just removed them. And we thought, how can we introduce various aspects of AI and machine learning models into this process to automate a lot of it? So under data capture, we're nominating to get rid of topographical surveys and just put mobile mapping panoramic imagery with automatic segmentation with a direct to GIS map overlay procedure. From there then in the data processing, we want to automate the image semantic segmentation material classes and then produce vector-based shape files from those material classes that then get published onto a GIS map in the correct coordinate system. From there, those vectors are passed across into the design environment automatically, where the creation of the design options can happen as per existing design processes. And then a series of LLM-produced auto lists are run automatically to compiled the critical reporting design options, and published them through to the large language model that was vertically trained on a set of heuristics, which will automate the analysis of the extracted design data. It'll automate the assumptions and contingencies accurately from an early stage design development, and it'll give you your actual deliverables of your bill of quantities, or it'll give you in real time value engineering insights. So in order to realize this hypothetical workflow, we had to actually understand which machine models we could nominate. So initially for the data capture, you do need a GIS capable 360-degree car mounted camera. And then for the data processing, we nominated the street service viz data set in combination of the seg-former transformer model. Understand that that was actually after a number of sequential reviews of different options and different tests that we came to that conclusion. The shapefile material class then had to have the metadata stored under the geodata frame label storage, so that that information via Python script could be published across the different design environments or the different environments. So the vector shapefiles had an association to the label data. So when we went from QGIS map then into the design development environment, we could automate the data import, the design option reviews, and the data extraction. And then the heuristically trained large language model could automatically give us our interpretation of our costs. And looking at the small scale work sample idealized, we think that the 3-month development pipeline can reduce down to a 1.5-month timeline. And if you're a typical design consultancy who's working on a 20% net profit margin, give or take, you can expect an increase to your margins of up to 100% without additional labor, assets, or resources. So results, going through the actual case study itself in Canberg, right? So the first thing was the actual nomination of the data set, the changing of the data set functionality for the reporting criteria. So we chose a data set that had more material classifications identified than what we'd like. So we actually had to untrain and retrain the original data set, or inform the original data set. So the 5 material classes here were the ones nominated for this exercise to validate the proof of concept, and they were given their own color designation. So as you can see, the semantic segmentation was actually aligned with the color classifications required on the right-hand side. So the seg-former model was trained iteratively, and you can see that it correctly learned how to distinguish the difference between the paving stones and the actual smaller set stones of different patterns. But it did have errors which consisted of the building themselves, the elevations were automatically segmented into the concrete class, for instance, or that you could see here there was a segment shift due to the 360-degree nature of the panoramic images. But that was less concern once we got to the 2D map overlay. It actually still mapped correctly. So speaking of the 2D vector overlay, publishing this data through to GIS and going through multiple iterations of that workflow, you could see that the actual road network and the crossover surfaces were starting to be developed accurately, and that we were actually able to get correct segmentation publishing down onto the map. So when we go through from our design environment, we nominated a single vectorized segment to do a proof of concept, where we published that to an ordnance system through GIS straight into the vector design environment. And you can see that the paving aligned perfectly within the paving hatch from the design environment. And you, as a proof of concept, you imagine you did that for the myriad of the panoramic images, and then you have an actual automatically building of the map on the design environment in a vector-based format, correctly identifying all the material classifications and their various data sets. Then from there, the design options 1 and 2 were generated as proof of concept for the area, and we were able to run a series of auto lists that broke down those design concepts and all the various service types within them and the various line lengths under each material classification into a table of lengths, which were then published via CSV into the vertically trained LLM, which gave us our cost efficiency ranking, our suggested narrative and the most efficient design cost option, a breakdown of the percentiles on both cost options, and also gave critical insights like the percentage of road crossovers, which can be very disruptive in an urban context. Finally, in terms of production of deliverables, the vertically trained LLM was able to deliver us a total cost, the full line item breakdown and percentage of each service run nominated, summary key cost insights, conclusions, recommendations, and also isolated the service line 1 as a snap. So looking at the overall data set map for everything that was tested and validated, you can see it here. We're not going to go through this in this call, but it was very complex and very detailed for each of the 3 primary workflow stages that we had at machine learning model implementations. And then the process map, moving on from what was the hypothetical to the detailed, we basically had the nomination of the street surface viz data set, which then went through multiple training cycles in the seg-former transformer machine learning model, which then vectorized the material class segments, so they could be published and overlaid onto a 2D GIS map in QGIS, which then was able to marry via an exchange with a AutoCAD vector-based environment, which was set up in line with the material heuristics, and then publish that data from the design options developed into an LLM, and straight into cost-effective proposals and reporting. So very quickly, I'm not sure how much time I have now, but I'll just go down to the conclusions. So the results, basically, we validated the entire workflow for what a business is. We showed that we could take every stage of that and improve it and condense the overall workflow and improve the ROI. There was successes and failures in every aspect of that. There were successes for the model training for differentiation to different set classes. Would you like me to continue? Yeah.
You can take a
There
few
was
more seconds.
Yeah, okay. There was a mobile mapping imagery segmentation and visualized GIS CAD tool. So that mapping imagery came all across all the tool set through all the workflow. We did realize the automated value engineering design and reporting in the design environment and the extraction of that information. And we did realize the BOQ report generation. So the limitations, Segform struggled with the distinguishing asphalt and concrete because the shades of gray, it was just struggling to actually nominate that, and that just needs further development. The equation that informs the panoramic imagery mapping to the GIS map is quite complex and would need completion to automate that workflow in full. The auto-list generation testing cycles were arduous with the GPT-4 model that we were vertically training, hallucinating and forgetting previously defined parameters. The vertical training of the GPT-4 Omni large language model, it would lose its context. So we kept having to repeat the prompts consistently to inform that correctly to finalize it. The observed benefits, we can realize that 50% time implementation to the same output if this full process is, that's the key insight here. It's all validated and it can be further developed to get there. And then the potential opportunities are basically the inverse of the observed limitations, whereby if we utilize, let's say, manually labeled masks, we might improve the segformer issues that it's struggling with. The completion of the equation will automate that full panoramic image to QGIS 2D mapping algorithm. We also have the overall combined auto Lisp could be no different than Group 6 implemented as a plugin now for those who are not Lisp literate. And then the standardized framework should be developed for informing the vertical training of LLMs so that they don't lose the context you've already previously informed them for. So thank you for your attention, and that was quite quick, so apologies.